When we first started learning how to graph lines or quadratics or cubics or anything else, we started by creating a chart where we would record some input values and then calculate what the output value was for each one of those input values and record those as well. Each pair of these gave us a point on the graph, and that's exactly what we're going to do with our sine graph, except that with sine and cosine and the other trigonometric functions, it's more common to use theta as our input. So I'm going to do that here, although you should be aware that you can actually use x as your input variable, and sometimes you will see that. In fact, it's not uncommon when you're dealing with trigonometric functions in an algebraic setting to see x as the input variable instead of theta. Either will work. So what kind of input variables do we have for sine? Well, we know some nice values. We have pi over 4, pi over 6, and pi over 3. And then we have 0 and pi over 2 as well. Beyond that, we know that we can graph in all 4 quadrants using the circular approach by just changing the sign, S-I-G-N, of the answer. For our sine function, the answer was always positive if it fell in quadrant 1, if the angle fell in quadrant 1 or quadrant 2. If the angle fell in quadrant 3 or quadrant 4, it was negative. Well, I'm going to start here by graphing just the values for the sine of theta that fell in quadrant 1, just so we can get an idea of how this process is going to work. And then we'll come back and we'll make an analogy to the circular graph. Okay, here are the first few values of theta that I'm going to use as input values to graph the function, y equals the sine of x. I'm going to go, let's see, I think I'll do it in the bottom right-hand corner. I'm going to remind us about our values for these functions. This might come in handy later as well. So this is my theta, and the sine of theta is 0 when theta is 0, 1/2 when theta is pi over 6, root 2 over 2 when theta is pi over 4, root 3 over 2 when theta is pi over 3, and 1 when theta is pi over 2. So we know both our input values, which match these input values here, and the corresponding output values. So really all I need to do is take these values and put them in this chart. Let's do that. 0, 1/2, root 2 over 2, root 3 over 2, and 1. Now, how do you graph these? Some of them are easy. 0, 0 is just the origin. This height of 1/2 occurs at pi over 6. I don't have a pi over 6 here yet, so I'll come back to that one. At pi over 2, I have a height of 1. So if you can see, here's pi. So half of that is this one right here. That's pi over 2. So at pi over 2, I'm up at 1. And I don't know anything else yet, right? I have a 0 and a pi over 2. Those are my extreme input values. Sorry, pi over 2 is here. Everything else has to fall from here, has to fall between those two values. So the next thing to do is to figure out what the approximations are for these two things so that I can graph them. The purpose here is just to get a visual on what the graph of this thing looks like. So I need some approximate values for these two exact values so that I can plot those points. The other thing I'm going to need to do is I'm going to need to insert pi over 6 and pi over 3. Right now I have 0, pi over 2. This would be pi over 4, but there's no pi over 6 or pi over 3. Now I've intentionally left those off so that I can plot them in. They are not exactly halfway between 0 and pi over 4. They are closer to there in relation to pi over 4. In the same way that in quadrant 1, if this is pi over 4, or 45 degrees, 30 degrees is not halfway between, but more like here, pi over 6 rather, and pi over 3 is just the other side of it. There's a much bigger angle here than there is here. Now, this is slightly exaggerated. This is not completely accurate, but my point is that the space between these two and the space between these two tick marks is much smaller than the spaces on either side. So be careful with that. All right, now that I've graphed that, now that I've added the pi over 6 and pi over 3, I can use this pi over 6 comma 1/2, this point right here, I can plot that one. That's going to be right about here. Pi over 6, remember, is the same as 30 degrees. And then I need to go get decimal approximations for these two. Just sticking them in the calculator gives me these values. Now, the root 2 over 2 is actually 0.707167812 and so on. And root 3 over 2 has an equally long approximation on my calculator screen. But for the purposes of graphing these, I am not going to be able to use anything more than about 1/10. So I'm just going to say that root 2 over 2 is about 7. And so that means that I have the point pi over 4 for my input value, my x or my theta value, and the output value is about 0.7. Well, 0.7 is more than 1/2, which is 0.5. So I'm going to be up about here somewhere. Right about there. And then for pi over 3, which is 60 degrees, that's this tick mark right here, I'm at 0.86 or almost 0.9. So we'll put that point above this tick mark here, right about there. Now, if you're familiar with what the graph of sine of this y equals the sine of x or y equals the sine of theta looks like, I'm having trouble getting this in just the right spot here, kind of going over it a couple times. If you're familiar with the graph of sine, then you'll begin to see what that familiar curve looks like. And you know what's going to happen next, right? It's going to come down here and then go below the x-axis and come back. But even if you are familiar with this graph, I want to remind you where the shape comes from and why it does what it does. So that's why I'm doing this piece right now. Now, the next thing to look at is what happens next, right? What happens after pi over 2, but before pi? Well, let me remind you that we had angles that look like this in quadrant 1, and that was 30 or pi over 6, 45 or pi over 4, 60 or pi over 3, 90 or pi over 2, and that's where we are so far, right? We have 0, 30, 45, 60, and 90. The next one is, well, the next one I could do is this one here, or I could go to pi. I'm also going to need to add some tick marks either side of my, this one right here. This one's pi, this is halfway between 0 and pi, so this is pi over 2. I know I could label them, but it gets very, very messy very fast. Halfway between 0 and this one is pi over 4, so that one's pi over 4. This one's pi over 6, and this one's pi over 3. So between half of a pi and a whole pi is 3/4 of a pi, so that's 3 pi over 4 right there. And I'll leave it at that. The ones either side are the one, like pi over 4, the one just before that is pi over 6. This is the same equivalent distance here. So the next angles in my circle would be from 90, add another 30 degrees, add another 45 degrees, add another 60 degrees, add another 90 degrees. And that gives us angles. There's the 45, hang on. There's the 45, there's the 30, and there's the 60. Now these are 30, 45, and 60 more than 90, right? So we're going to have a reference angle here, one for the 30, one for the 45, and one for the 60. And those reference angles are going to have the same sign, S-I-N-E, the same values for sine as the original 30, 45, and 60. Let's take a second and remind ourselves what those angles are called. We had pi over 4 here. This was pi over 2. And if I travel another 45 degrees or another pi over 4, I've got 1 pi over 4 here, 2 pi over 4s here. This is 3 pi over 4. Now, if I go in terms of pi over 6s, I have 1 pi over 6 here. There's a second pi over 6. That was 2 pi over 6. 2 pi over 6 reduces to pi over 3. I'll go ahead and write those in. This one was pi over 6. This one was pi over 3. Go another pi over 6 from here, and you get 3 pi over 6. So that reduces to pi over 2. Another pi over 6 is, from 3 pi over 6 is 4 pi over 6. That's 2 pi over 3. And one more pi over 6, that gives me 5 pi over 6. That doesn't reduce, so I have 5 pi over 6. And so those are the next angle values, input values I want to use for graphing my sine function. The nice thing about this is that I can take, oh my goodness, I have to do this a little bit at a time apparently. My apologies. If you'll recall, my pen does not, or my software does not let me move things and then come back. It puts them back in their original position. So I have to move them on screen if I want to move them at all. So one thing I could do here is say, well, that was quadrant 1. Let's go ahead and look at quadrant 2, and I could start putting in my values for quadrant 2. My next one would be 2 pi over 3. Then I'd have 3 pi over 4, and then 5 pi over 6. And I didn't add this one, but I should. In terms of pi over 6's, I get to 5 pi over 6 here. Add one more, and you get to 6 pi over 6. Well, that's just pi. And we know that 180 is equal to pi. So those are my new input values. So I'm going to go ahead and graph those. Now I could just put sine of pi over 2 pi over 3 into my calculator, and it would spit out a decimal value, and I could say, well, that's, let's see, 2 pi over 3 is this one right here, and I would get a value, and I could plot that point. But I don't want to do it that way here, because I want to use this as an opportunity to remind you that we know what the sine of 2 pi over 3 is, because we know what the sine of its reference angle is here. Now, its reference angle is equivalent to 60 degrees, so it's equivalent to pi over 3. So the sine of 2 pi over 3, I'm doing this because I'm imagining a vertical. What I should be doing is saying this angle right here, right? Make a different color. This angle right here is a 60-degree angle, or a pi over 3 angle. So what is its sine? Its sine is the same as pi over 3, which we know to be the square root of 3 over 2, or 0.866. And we know it has the same plus or minus sign as well, because we're in quadrant 1 and quadrant 2 for sine. All ratios are positive in quadrant 1. Sine is positive in quadrant 2. I have to think for a second. It's T for take. All students take calculus. So tangent is positive in quadrant 3, and cosine in quadrant 4. And since we're in quadrant 2 at the moment, and we're dealing with sine, we know that all our values are going to be positive, and they're going to have the same numerical values as the values in the first quadrant. So where I had a reference angle of pi over 3, which is this one right here, that's the big one, that's 60, that's a third of pi, that's 60 degrees, it's going to have the same value as this pi over 3. For 3 pi over 4, well, that's a multiple of pi over 4, right? My reference angle here, maybe I'll do it in like a pen, but a different color of pen. This angle right here, that's pi over 4. The reference angle is pi over 4. And we know that the sine of pi over 4 is about 0.7071. And again, we don't really need all of that because we're just approximating those values on a graph. I don't even have any vertical tick marks, so I'm really kind of eyeballing it. And then we have, I need a different color again. Maybe I'll use green. Then we have this reference angle, and that's a small one. That's a 30-degree reference angle, so that's pi over 6. The sine of pi over 6 is a half, so the sine of this pi over 6, this 5 pi over 6, is also going to be a half, and we also know that to be positive because, again, we're still in quadrants 1 and 2. Sine is positive in quadrants 1 and 2. Lastly, we haven't talked about this yet, but pi, which is 180 degrees, right? That's 6 pi over 6, or 4 pi over 4s. The sine there is 0. And one of the ways of thinking about that is that the reference angle here is also 0, right? If you imagine this terminal side here coming and landing right on the x-axis, on the other side of the x-axis, well, it kind of closes the gap there. So my reference angle there is 0. My reference angle, or my real angle 0 over here, has a sine of 0. So my reference angle of 0 is also going to have a 0. Is also going to have a sine of 0. Another way to think about this, and I'll just put this up here kind of quickly, just as a demonstration. If you have the angle 0 radians or degrees, right? There's an angle of about a half of a degree, or maybe 1 degree. But if you imagine closing that gap here, right? Think about what the opposite side has to be. If that terminal ray is sitting down right on top of, in the exact same position as the initial ray, then the opposite side here has a length of 0. All right, this one's exaggerated slightly because it's actually slightly higher than the x-axis. If it was right on top of the x-axis, then that opposite side there would have a length of 0. And since sine is opposite over hypotenuse, well, that's going to be 0 over hypotenuse, and that's going to be 0. So that's one way of thinking of why the sine of 0 is 0. Okay, so now we have some more values down here, some x, y, or theta y coordinates. So let's go ahead and plot those. Before I do, though, I want to make this analogy. Let me grab a different color again. I'll use green. If I go from 0 to pi over 2 in this circular representation of sine, right, circular representation of angles, then I'm going from 0 to pi over 2, which corresponds on my new graph as being, I'm trying to decide what color to use here, between 0 and pi over 2. Then I'm going to go from pi over 2 to pi, so that takes me from pi over 2 in the x direction, or the theta direction, pi over 2 to pi. So for my first quadrant, let's use a white highlighter. I was in my first quadrant. I'm kind of in this first band, if you will, of theta values, input or x values. For my second quadrant, I'm using a yellow highlighter in the circular diagram. I go from pi over 2 to pi, and that takes me here from pi over 2 up to pi. So the second quadrant can be represented in this way. This is the first quadrant, this is the second quadrant. And I can do the same with the third and fourth quadrants. Let me add a few more angle values here. This one's going to be 2 pi. And if we think in terms of pi over 2's, that's just how it's going to be convenient initially to divide this axis up. I have 1 pi over 2, 2 pi over 2's, 3 pi over 2's. You can think of this as 3 pi over 2's, but that's just 3 pi over 2 because of the way multiplication works. So I have 3 pi over 2, and then of course 4 pi over 2. Now, if I think in terms of pi over 4's, I have 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. And then, of course, I'll have my 30 and 60 degree, or pi over 6 and pi over 3 radian reference angles as well. Okay, so now we've labeled our axis a little bit more accurately. Let's go back and plot these points here. For the angle 2 pi over 3, because it has a reference angle of pi over 3, we know its sine is 0.866. Well, that's about 0.9. So I'll plot that here. 2 pi over 3 is this tick mark right here. So when theta is 2 pi over 3, we know that y has a height of 0.86 or almost 0.9. So that's going to have the same height as the pi over 3 tick mark point had. So that puts us about here. then 3 pi over 4 has a height of about 0.7, which is the same height as the pi over 4 point. So that puts us about there. 5 pi over 6 has a height of 1/2, and pi has a height of 0. Now, there are angles between 0 and pi over 6, between pi over 6 and pi over 4. So there are points in between here as well. But this is enough to give us an idea of the pattern that's happening. The graph of the sine of theta looks something like this, at least between 0 and pi. Okay, that's not the greatest sine graph I've ever drawn, but it'll do for my illustration here. All right, now we need to do the same thing for the angles between pi and 2 pi. And I'm going to split that up between pi and 3 pi over 2, and between 3 pi over 2 and 2 pi. And the reason for that is that the angles between pi and 3 pi over 2 are in quadrant 3. And then between 3 pi over 2 and 2 pi, I'll be in quadrant 4. So that's why I'm separating things out the way I am. That's supposed to be green. There we go. Now, the nice thing is that I know that the values in quadrants 3 and 4 are the same as the values in quadrants 1 and 2, except down here for sine, those values will be negative. So I have to check and see where my reference angles are. This would be my 45-degree reference angle, which is pi over 4. Here's pi over 6, which is 30 degrees. Let's just take a look at that one and see what happens. This is a reference angle of 30 degrees, pi over 6. So I'm going to have a y value of 1/2, but I'm in quadrants below the x-axis. Over here, my opposite is negative. The hypotenuse is still positive, but my opposite is negative. So I'm going to have the same value as pi over 6, which is 1/2, but it's going to be negative. So at, what is that? 7 pi over 6. So there's 6 pi over 6's. There's 7 pi over 6. I'm going to be below the x-axis by 1/2. That puts me about here. And the next one's pi over 4. 45 degrees is pi over 4. Pi over 4 has about a 0.7 height, but because I'm in quadrant 3, I'm going to be below the x-axis. So at about 0.7, I think I'd be about there. Then the next one is, let's see, I'm thinking now in terms of pi over 6 pi over 6, 7 pi over 6. I'm thinking in terms of pi over 3s. This would be 3 pi over 3, so this one's going to be 4 pi over 3. Sorry, wrong pen. 4 pi over 3. This one was 7 pi over 6. All right, so for 4 pi over 3, I don't have that drawn down here yet. The angle, let's highlight it with something. Oh, I'll use pink. This angle right here, this is a reference angle of pi over 3. It's that size. Pi over 3 is a 60-degree angle. And it is about 0.86. The sine of pi over 3 is about 0.86. So I'm going to be about 0.86 or almost 0.9, but it's negative. So my y value here is going to be below the x-axis, about 0.9, not quite to 1, about 0.9, right about there. Now the next angle, we've done up to here so far. The next angle is this one down here. And the name of that angle, if I have 1 pi over 2, 2 pi over 2, which is pi, that's 180. This would be 3 pi over 2. So that's 3 pi over 2. It's the border angle. Sorry, I was using the wrong pen there again. 3 pi over 2. That's the border angle between quadrants 3 and 4. So that's this angle right here. The reference angle for 3 pi over 2 is 1 pi over 2. So all I need to do to find the sine of 3 pi over 2 is find the sine of 1 pi over 2, which is 1, and change its plus or minus, change its sign to a negative. So I'm going to have a negative 1 at 3 pi over 2. When I go into quadrant 4, I have, there's my 45. I always find it easier to graph the 45 angle first and then the 60 and the 90 either side of it. So I'm struggling to do that right now. There we go, that'll do. So my angle names here are 3 pi over 2. If I go in terms of pi over 2s, I have 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. These are all pi over 2 angles. They're all 90-degree angles. But 4 pi over 2 is 2 pi. Well, I've done up to 3 pi over 2. I'll come back to 2 pi in just a minute. Now I need to do the ones in between. So let's go with the 45s. I have 1 pi over 4, 2 pi over 4. Each one of these is a 45 pi over 4 angle. 3 pi over 4, 4 pi over 4, which is pi, 5 pi over 4. I didn't label it here, but I did label it up here. 5 pi over 4, 6 pi over 4 is 3 pi over 2. 7 pi over 4, that's going to be 7 pi over 4. And that goes in here. I've already got it labeled. If I think in terms of pi over 6's, I get 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, which is 3 pi over 2, 10 pi over 6, which is 5 pi over 3. So this one is going to be 5 pi over 3, and that corresponds to this angle right here. I can't get that, I can't squeeze that in there. 5 pi over 3. One more pi over 6 gives me, that was 10, 11 pi over 6. So this angle is 11 pi over 6, and that corresponds to this one right here, 11 pi over 6. And lastly, 12 pi over 6, which is 2 pi. Okay, so the same thing applies here. My reference angle, I'll just go with this one first of all. The first one I come to is a 60-degree or a pi over 3 reference angle. So the sine of 5 pi over 3 is going to be the same as the sine of pi over 3, except that it will be negative. So negative 0.9, 5 pi over 3, find the 5 pi over 3 and go negative 0.9. Then the 45 or pi over 4 reference angle, color that one in blue. It's going to be this angle. Okay, that's going to have the same sign as pi over 4. The sine of pi over 4 is about 0.7, but it's in quadrant 4, so it has to be negative. So I'm at, where am I? 7 pi over 4, I'm at negative 0.7, which is right about there. Then I'm at 11 pi over 6. 11 pi over 6 has the same, it has a reference angle of pi over 6 because, let me go ahead and color it in. I think I'll do it in pink. All right, my reference angle here is 30 degrees or pi over 6. So the sine of 11 pi over 6 will be the same numerically as the sine of pi over 6. So that's a half, but because it's in quadrant 4, it's negative. So I'm at negative a half. And then last but not least, for now, we come all the way around to 2 pi, but 2 pi is the same as 0. That the sine of 0 is equal to the sine of 2 pi. And even if you make it negative, it's going to be 0. So I'll put a dot there. And so from this, you can see that the pattern kind of continues. And that is one, I don't know what to call it at this point because we haven't talked about some of this terminology, but we might as well start. So what we call one period of the graph sine, the sine of theta. One of the wonderful things about graphs like this is that once you get from 0 all the way down around and back up to 2 pi, what's happened is you've gone around the circle. If you add angles out here beyond 2 pi, let's see, the first one would be 2 pi plus pi over 6. And that's 12 pi over 6 plus pi over 6. That's 13 pi over 6. That would be sort of in there somewhere. Put a tick mark there. That's my input, 13 pi over 6, but I have started over, right? It's like saying, okay, there's 2 pi now. Pi over 6, that's 13 pi over 6. They're coterminal. So of course they're going to have the same sign values, and so I'm going to have another point at a half. And this graph then just continues forever, going up and down and up and down. One of the things to notice is that it never gets above 1, and it never gets below -1. My graphing skills with no graph paper here are somewhat limited, so I don't know how well I actually capture that. That should be maybe be, no, that's not too bad. And 1, yeah, I didn't do too badly there. So this graph goes up to 1 and never gets any higher, and it comes down to -1 and it never gets any lower. Okay, it just keeps repeating. And it keeps repeating in the other direction as well. It's as though I said, let's go backwards, right? We'd start with this reference angle, and then that one, and then that one, and so on. And so because of that, first of all, I'm going to be negative, and then negative, and then positive, and then positive. And so I'll have points on this side that match the points on this side, but they'll be upside down, right? Because here, when I went this direction, I was positive and then positive. So I was positive and then positive, and then negative and negative, negative and negative. If I go backwards, then I'm negative and negative, so I'll be down here. And so my values will still match, but my graph will be upside down. So at the reference angle of pi, I'll be at 0, and at the reference angle of 2 pi, I'll be at 0. Halfway in between 0 and pi and 2 pi, I was either at 1 or -1. So because I was up here, I'm going to be down on this side at -1 at the halfway point, and I'll be at +1 on the other side. Okay, now let's take a look at some of these other reference angles. I went from 0 in terms of theta. I went from 0 to pi over 6 to pi over 4 to pi over 3 to pi over 2. And in terms of the sign for each of those, I went from 0 to a half, to about 0.7 to about 0.9 to 1. So I'm going to do the same thing here, but it'll be negative. So I'm going to be at a half for pi over 6. Now that's my reference angle, pi over 6. That's actually negative pi over 6. And then 0.7, and then 0.9, and then 0.9, 0.7, and 0.5 before I go back to 0. Then I'll be at 0.5, 0.7, 0.9, 0.9, 0.7, 0.5. And the graph continues. It looks something like this. And as with the other side, if I wanted to, I could say, okay, now that I've got all the way back to, where am I? All the way back from 0 all the way back to -2 pi. What happens if I keep going? Well, it's just going to keep repeating itself. So this graph will continue indefinitely. We call this a periodic graph or a periodic function because you can take one cycle, if you will, we call that a period, take this one period, and if you could copy and paste this, that would be enough to get the entirety of this graph. Of course, you'd have to be pasting forever, but the point is that this one cycle just keeps repeating itself over and over and over again. You can actually see that right here. If I could pick this up and copy it over here, I wouldn't have had to plot those points. Well, I did the first time because I need to know that's what's going to happen, right? But now that I know that that's what the pattern is going to be, I can copy it and paste it over here. I can paste it here, I can paste it back here, right? So we call this a periodic function. And one of the really interesting algebraic, very useful algebraic things that we can say is that for any angle any angle theta, that's going to be equal to the sine of any angle theta plus 2 pi. That means I can take any angle, I'll do it here, I'll take any angle theta, I'll figure out what its sine is, and if I plug theta in here, I'll get theta plus 2 pi. The sine of that angle is going to be the same as the sine of the smaller angle. Let me show you what I mean. We know that the sine of 0 is 0, right? That's plotted as a point here. If the input is 0 radians rather, the output is y equals 0. So sine of 0 is equal to 0. If I put a 0 in here, I get 0 plus 2 pi, which is 2 pi, and the sine of 2 pi is also 0. Maybe that one's too obvious. Let's try pi over 3. If I put pi over 3 in here, I get about 0.9. We found that down here. The sine of pi over 3 is 0.9. Add 2 pi to pi over 3, you get 2 pi plus pi over 3 more, and the sine of that is going to be 0.9. I haven't proved that to you here, but you can see from the pattern the graph is making that that makes sense. All right, there's one more piece of vocabulary. It's actually something we've already talked about, but I just want to extend it just a little bit. We've talked about the fact that the period of sine is basically the amount of space it takes to do one cycle. On the graph, it's what is one cycle, right? But what we say about that then is that the period of sine is the amount of x-axis or theta axis we have to cover to do that. So we're going to say that the period of sine is 2 pi. Sine has a period of 2 pi. That's how long it takes to get, not from where you start to where you end, because we start at 0, we end at 0 here, but we're not done, right? This is a different pattern than we saw over here. This is positive, this is negative. We have to get all the way back to a place where now, if I start here, I'm going to get this same wave again, right? I'm going to start by going up, and then it'll come back down and come back up to 0. So this right here is a full cycle, a full period of sine, and it takes a full 2 pi to get from 0 back to 0 at a place where we're going to start over. Okay, so that's why we call that's why we say that the period of sine is 2 pi. Now, I've done a lot with this one graph. We still need to graph the function y equals the cosine of theta. I'm going to do that on this video, but I'm going to do it a lot more quickly. And as we get going on the next slide, you'll see why. Okay, here I have the same setup as I did on the previous screen, but this time we're going to graph y equals the cosine of x. We know from our table of values, from the work that we've done earlier this quarter, that we have some of these same values for cosine of x as we did for sine of x. And I don't know if you've noticed this, but if you memorize the row that has the sine values in it between 0 and pi over 2, all you have to do is reverse that to get cosine. That's pretty cool. The other thing that I like to point out usually around this time is that you have the square root of 2 here, the square root of 3 here. If you wanted to, you could think of this as the square root of 1 over 2. And you could think of this as the square root of 0 over 2. And you could think of this as the square root of 4 over 2. So as long as you have it over 2, you just take the square root of 0, 1, 2, 3, and 4, and you have your first 5 values, right? The sine of 0 is 0. The sine of pi over 6 is 1/2, but there's another way to think of it. And then just reverse those values and you'll get the cosine. Well, we're interested in the cosine here, so we're going to plot at 0, at theta equals 0, cosine equals 1. So I'll put that in my table. When theta equals pi over 6, I get root 3 over 2 for cosine. The cosine of pi over 4 is root 2 over 2. The cosine of pi over 3 is 1/2, and the cosine of pi over 2 is 0. Now remember from our previous screen also that this is about 0.866, and this is about 0.7071. Really, I think I'm just going to go with 0.9 and 0.7. It's an approximation in the first place, and I'm getting away with rounding it as much as I am because I'm literally just grabbing a quick visual guide to what the graph looks like. I'm not trying to graph this to any level of accuracy over 0.1, right, 1/10. It's really kind of impossible to do that. Even with a super sharp pencil, you'd be lucky to get any more accurate than 1/10. So let's plot these points. I have 0, well, I don't have my ones here. Let's go 1 and -1. At 0, cosine is 1. I'll skip to pi. Oh, I don't have pi yet. Here's pi over 2. I'll go to pi over 2. At pi over 2, cosine is 0. At pi over 4, which is halfway between 0 and pi over 2, cosine is about 0.7. And then 30 and 60 fall on either side of 45. Pi over 6 and pi over 3 fall on either side of pi over 4. Well, at pi over 6, I'm at about 0.9. And at pi over 3, cosine is at about, that should be a 1/2, not a 1/3. My apologies. Pi over 3, cosine of pi over 3 is a half, so I'll be about there. And I have something that looks like that. If I continue, that was quadrant 1. There's pi over 4, pi over 6, and pi over 3. And so I have 0, pi over 6, pi over 4, pi over 3, and pi over 2 for cosine. And now I'm going to go into quadrant 2. There's my 45, or pi over 4. And these are my reference angles, pi over 6 and pi over 3 for quadrant 2. But remember that all ratios, all trigonometric ratios are positive in quadrant 1, but only sine is positive in quadrant 2. Only tangent in quadrant 3 and only cosine in quadrant 4. So let's do that again here. We'll split the graph up between quadrants. And I can't remember what colors I used on the previous screen, so I'm going to have to punt here. I'm pretty sure I used white for quadrant 1. And after that, I've forgotten. I'll just go down here. We'll go pink for quadrant 2. That means quadrant 2 here. I'll use blue for quadrant 3. That's quadrant 3. Here's quadrant 1. And maybe yellow for quadrant 4. I'm just taking these quadrant sort of divisions from the fact that I'm going from 0 to pi over 2. In a circular motion, that looks like this, 0 to pi over 2. But in terms of what is my theta, what is my input here, it looks more like 0 to pi over 2. And then quadrant 2 starts at pi over 2 and ends at pi over 2 to pi. That's all I'm doing there. Now, because I know sine is positive in quadrant 2, and only sine and cosecant, because it's related, sine and cosecant are positive in quadrant 2, but everything else is negative. So I already know my graph for cosine is going to be down here in quadrant 2. And if I look at quadrant 2 here, look, I've gone from 0 to pi over 2. Now I'm going to go from pi over 2 to pi. Let's just go straight to pi. Let's talk about what the reference angle is at pi. The reference angle is the one that has an opposite of 0 and an adjacent that's the same size as the radius. Right? So I'm going to have adjacent over hypotenuse as the length of it's just going to be the radius over itself. Adjacent is the same as the radius, so adjacent over hypotenuse is adjacent over adjacent, or hypotenuse over hypotenuse, which is 1. Right, so at pi, my cosine is going to be 1. And let's see, at pi, but I'm in quadrant 2, right? I've come through quadrant 2. So I'm negative here. And cosine's negative in the next quadrant anyway, so I have to be in this region here, between the pink and the blue quadrants, between the pink and the blue regions, everything's negative. So I'm going to be down here at -1. And in between, at my reference angle of pi over 4, well, that's at 0.7, but it's negative. So I'm about here. At my reference angle of pi over 6, I'll be at 0.5, and at my reference angle of pi over 3, I'll be at 0.9. So I get something that looks like that. And then I can just carry on. I'm not going to bore you with this. You've already seen me do this once with sine, and I know that the actual plotting of points is pretty tedious to, it's tedious to do. I imagine it's even more tedious just to watch. But I will say this. Once you know what sine and cosine look like, and the fact that sine started here at 0, went up to 1, and then came back, and cosine starts at 1 and comes down, you can plot the 1, the 0, the negative 1, the 0, and the 1. And you know that the graph has to fit that pattern. Moreover, it will continue in the same way. Now watch this. I went from 1, and I'm going to end at 1 also. So for one cycle, I'm going to start at 1 and end at 1. Halfway in between, I'm at the opposite extreme. That's negative 1. Halfway in between each of those, I'm at 0. There's kind of a graphing tip. When you graph these, be sure not to draw straight lines like that, because that is not what the graph looks like, as you can see from the work that I've already done, right? These are not straight lines with pointy ends. They curve at the top, come through 0, and then curve at the bottom. That's terrible, but you get the idea. Now, can you tell me what the period of cosine is? The period of cosine is also 2 pi, because that's how long it takes to get from the beginning of a cycle to the end of a cycle to a place where you can start over again. I've kind of messed up my highlighting here, but hopefully you get the idea. That is over exaggerated, but that is the amount of space one cycle for cosine takes. It starts here and it starts over here. But when we look at it in terms of the input values, the theta axis, we say, well, that took 2 pi. So the period of cosine, I'll write it this way this time, cosine has a period of 2 pi. Or you can say that the period for cosine, or the period of cosine, is 2 pi.